Hey everyone, thank you all so much for coming to this webinar about optimizing big data workloads. We're Granulate, we're a real-time continuous optimization company. And in this webinar, we'd like to share how we optimize and improve any big data workloads. So with that, let's get started and jump right in. So first, an introduction. My name is Gruner. I'm the VP R&D of Granulate. Joining me here is Sobol, who is the team lead. So as I've said, we are Granulate. We are a real-time continuous optimization company. Basically, we've developed a technology that through changes in the operating system and the application level to better prioritize and manage the resources of the machine is able to improve the performance, reduce costs by about 60% or the job completion time of 40% while requiring absolutely zero code changes or R&D efforts.
Okay, so let's get a bit into big data and how it works. So big data basically has 4 building blocks or parts. It has the collection, the processing, storing, and visualization. Sorry. The main resource consuming parts are the ones on the start, the data collection and data processing. This is the main place where Granulate optimizes and works, and where we see the most benefit in making things faster or work with less resources. Let's go ahead and see the architecture and types of big data. Okay, so we're walking into how big data works. As you can see, we have some names, some buzzwords in the big data names, and you can see a wide, complex, with vast changes over time, with names coming in and out, and an environment that is really complex and consists of very different approaches and solutions. You have connectors and data platforms and consumers, and each and every one of them has a lot of names and different approaches to how to solve the solution of big data. So Granulate actually works on all of them, and the reason it does will be explained later on when we just explain a bit about how Granulate works internally.
Yes, and continuing on the complexity of the issue, even there are many different use cases. So at large, there is the batch versus the streaming kind of use cases, where both presents a different kind of problem and performance issues and possible solutions. So in the batch kind of workloads, you usually read from an external storage, could be disk, HDFS, could be remote storage over S3, requiring the many accesses to the disk, many accesses to the networks. Very difficult to program, as you need to make sure that everything continues to work. You need to make sure reliability is solved for, and your application is robust in case of failure, in case of data loss, in case of problems in the compute resources. And on the other side, you have the streaming kind of way of doing things, where the data continues to come. You try to process it in real time or close to real time, process it, then it moves on to probably another step of the pipeline. And in these use cases, the main issues would probably memory consumption, as you need to hold most of the data in memory, excuse me. You need to handle it in a smart way. You need to make sure the pipeline flows in the correct way and is configured correctly. And many frameworks were built on top of it, so in many different languages. So Scala, Java, Python, PySpark, everything kind of is a mix between the two, and both present different challenges and opportunities. And obviously you can understand how, while similar in nature in what they do, they, however, do require different resource utilization patterns, different capacities, different programming styles that presents both challenges and opportunities. And when we're talking about optimization, cost saving, and things like that. And these complexities happens in many different ways. So there are challenges that are more specific to some of these use cases or to others, but they're pretty generalized pretty well into the entire big data world. So obviously everything requiring significant compute scales. There are many moving parts in the streaming instance, for example, but eventually everything is distributed. So everything needs to work, everything needs to be reliant, robust, handling the errors. Machines can fail, and that's why it's very complex. And that's why the frameworks themselves, Spark, Hadoop, everything that it encompasses the big data world is that complex. And this complexity hides a lot of things. There is lack of visibility. Getting the right observability tools into it is a challenge. There are many startups and many companies that are attempting to solve these challenges as well. This also leads to very unoptimized code because there is a lot of abstraction going on the underlying surface, on the underlying compute resources. And that's sort of the goal. But again, when you're looking at it through a performance improvement or cost saving kind of way, then it makes it incredibly hard to tackle the right places to understand where the time is going into and what you need to improve in order to save these costs. And so these are all the challenges which results in both increased compute cost, increased data storage costs or data transfer costs. And these are the bottom line costs, but they're also present in more development time, slow execution time requiring development or data analysts to try to take longer to try to analyze or understand data. And the entire cycle is taking longer because of that. So if you add a solution to better improve the costs, to reduce the costs, and to improve the bottom line, and to increase the software agility or a developer and data analyst productivity, I think that would be great, and that is what Granulate tries to achieve. But before we delve into the details of how Granulate works exactly, we should probably understand what current solutions are available as is in the world right now. So these challenges were already addressed in part in some ways. So as for the high costs or longer cycle time, people traditionally try to employ either provisioning, sizing the cluster, increasing the size to try to reduce or improve the performance of their calculation, or at least the time to get the results. Many work is currently done in companies that try to optimize this to find the correct instance size, to provision the right amount of resources. They're working at scale, so they try to get discount purchasing, spot instances or reserved instances at some point. Trying to build and find the absolute correct architecture, the most efficient one for their use cases. And when you get specific, you can get really good results. The problem, of course, is later on the agility aspect. When you try to change things, when you try to solve different kind of problems as the business requirements changes. And of course, even configuration tuning. So all those systems and all these frameworks have a large set of configurations, huge number of knobs that can be tuned and changed, and some tunings is obviously better than others. And many companies are trying to find the correct set of parameters to fit their application specifically. And having said that, even when taking all of that into account, even when trying to employ all of these techniques, they're still generally running at pretty low utilization, resulting in 2 to 5 times performance lost, what could have been achieved but isn't because of these challenges. And overall, we found that it takes 30 to 60% extra cost instead of being truly optimal. And even if we take different aspects such as configuration tuning, which, as I said, is turning the right knobs in order to increase the performance, the main issue there is that there are many knobs to turn. So in the hundreds or 1,000 knobs, getting to the correct configuration is often tedious and hard. There are several, obviously, companies that are trying to automate this process. They're trying to find the right set automatically, or at least an estimation of it, an approximation of it. But overall, the main problem is that it is not real time. It is either not real time, or that the return are diminishing over time. So you usually have the major improvements in the first few days once you try to find the correct set of knobs to turn. And later on, you can try to optimize it. You can try to further tune it to ever-changing workloads or use cases. But the general space is limited. So you have the knobs, you have the correct configuration, and that's it. And that is pretty limited because it doesn't allow you the absolute control over what the machine actually does in the operating system layer, or the connection between the operating system and the application framework itself. And this is exactly where Granulate comes into the picture. Our solution is a real-time continuous optimization that, as you can see, it works between the operating system and the application. That means that we try to understand, our agent tries to understand what the application attempts to do, and understand and prioritize the requests as they are then executed by the kernel, by the operating system, to better improve and enhance the performance of your application, whether these are jobs in Spark, Hadoop, or anything else really. And as we can see, we will show case studies later on, but we can expect significant cost reduction and increased performance, reducing job completion time, for example, reducing the CPU utilization, allowing to reduce the machine sizes, or the memory requirements, or the disk requirements. And all of this is with absolutely zero R&D efforts or any code changes. Briefly, how it works is you install the agent on the machine, and that's pretty much it. From that on, the agent starts in two major steps. The first step is where the Granulate agent tries to learn and analyze the application data flow and the different processing stages patterns. So in a big data world, this would usually mean trying to understand the different data flow, whether it is streaming, whether it is batch jobs, if it is loaded from disk, if it is downloaded from S3, how the different batches or streams move between the different processes on the machine, or the machines having its distributed cluster, and what kind of processing is done on the CPU for each of these batches or streams. And this could be divided into further. So this could, of course, rely on memory allocation. This could rely on Spark abstractions that can be better prioritized or changed. And this is exactly what we try to do in this step. Then taking this model and transforming it into prioritization, that we can activate the agent, and then the agent optimizes those OS resource levels, those application data flow, and different aspects of it to make better, more informed scheduling or prioritization decisions. And once you get this active and rolling, you can expect to get those significant cost reduction, the significant reduction in job completion time, and this increase in developer productivity and everything we described above.
Okay, so as Ron mentioned just a few slides ago, how Granulate product works, it makes its integration with everything much easier. Because unlike other optimization solutions, Granulate operates on the system levels and on the operating system, the Linux level, and it adapts dynamically its optimizations and its learning. It is infrastructure agnostic and integrates with all known architectures can, if it's cloud or if it's on premise, it works the same, and it grants you the benefits all the same if it's this or that. It makes it infrastructure agnostics and makes it easy to easily integrate with all architectures we know. If it's cloud or if it's premise, it works all the same. Okay, to sum it up, how Granulate gives the optimization, how it works on big data. It is infrastructure agnostics, means it works everywhere. The installation is very, very simple, single script, no code changes, no R&D effort at all. And it works with any past initiatives that worked on the machines or on the infrastructure. So Granulate can always just improve what you have there. And as I said, no code changes at all. R&D doesn't have to do anything. Okay, so we started with AppsFlyer, the first case study. AppsFlyer is a global large ad tech company. They have actually a cluster of self-managed Spark Hadoop data lake. In the AWS, a lot of machines work simultaneously on big data. And we actually managed to get a huge amount of improvement there. 25% reduced CPU utilization, 30% cost reduction, something that you can't get if you don't work the way Granulate works in EMRs. And I can add that in AppsFlyer, because they have large scale cluster, we're talking about 600 machines of R5 2x large, it means large machines and hundreds of machines. 30% cost reduction means hundreds of thousands a year in the total cost reduction. In the next slide, we can see how it looks where the client or the user looks at where Granulate works. You can see where Granulate is enabled, the CPU utilization shrunk by 25%, very large decrease. And then when we want to use this CPU utilization in cost reduction, we actually downscale the machines to 200 nodes instead of 300, which means downscaling a third, and the results of the CPU return to be the same as they were before, meaning 30% cost reduction.
Continuing to another, unfortunately can't disclose the name, but another Fortune 100 US-based company that is in the technology and mobility industry. Their use case was a bit different. They were running EMR on top of AWS, obviously, with a batch processing data analytics workload. And we were able to actually improve their workload by 44%, reduce the cost by that much. And this was a Python workload. So they were using PySpark as the main framework with over 20,000 cores. Mainly, as I said, downloading and uploading the data into the S3 storage engine. And in the next slide, we will be able to see the actual reduction in average job completion time. So on the left side, you can see in yellow the original, in red the same amount of time with Granulate agent in learning phase. So this is just an interesting demonstration that the learning phase doesn't change anything. It remains exactly the same with very, very minimal overhead. But on the right side, you can see the reduction significant, over 44 reduction in average job completion time. Obviously, you can imagine that some jobs were reduced even further, some a bit less, but overall, another great result. And to our final use case, another leading gaming company based in Israel with over $10 billion valuation. Their use case was entirely on-premise using Cloudera service. Again, batch processing. The underlying frameworks were Hadoop, Tez, and MapReduce. And we were able to, again, significantly cut the costs there, over 40%, reduce the CPU utilization over 25%, obviously allowing them to save on compute resources, reduce the amount of machines required, and reduce the paying bill eventually, while at the same time getting to a faster job completion time, which is pretty outstanding, allowing for, again, greater developer or data analyst velocity and more agility and better performance. And again, these are some graphs to demonstrate it. So on the left, you can see the CPU utilization reduction breakdown before Granulate and after Granulates. And on the right side, on the left, you can see that after Granulate and after the reduction, you can see that the average CPU is significantly reduced. On hard or extra busy moments in time, you can see that the reduction is reduced as well, that the average utilization is reduced as well. On the right-hand side, you can view the reduction in average job completion time. Again, in red is with Granulate, in blue is without, and you can see that there are significant savings there. Obviously, this changes per the use case or per the exact job workload, how it operates and how it works. But it's interesting to see that this is applicable to most of the jobs there. And overall, this results in the cost reduction and performance improvements. And so thank you very much. I hope that was a brief interview to Granulate and how we are able to improve and optimize big data workloads of any kind. And we welcome you to try to ask any questions. We would be happy to answer them. So stay in touch.